Section 14.3, the coefficient of determination. So what is the coefficient of determination? What is this for? And so we're going to learn in this section how to determine the coefficient of determination. And the idea behind this is to tell us if the regression equation that we found in the previous section, is that going to be useful or not for making predictions? That's what this section is about. Is we want to learn how to calculate the coefficient of determination. We call it R square. And we are going to see, based on the value we obtain, that will tell me about the regression line. If the regression line that we find the equation for is a very useful for making predictions or not. That's what this section is about. So to do so, we need to introduce new tools here. I call them new tools. Now, of course, always recall yi. We're going to use it throughout this chapter. Those are the y values, xi are the actual x values, y hat are the predicted y values, as we did in the previous section. Three new terms we need to introduce here. The first one is the SST, is the total sum of squares, the abbreviation for total sum of the squares. And it gives us the measure of the total variation in the observed values of the response variable. So that's defined as the sum of all the squares of the difference, as you can see, of yi's minus y bar. Y bar is the mean of all the y values. We have another term called the regression sum of the squares, SSR. This gives us the variation in observed values of the response value explained by the regression. And the formula is not just yi, but it's yi hat, so it's the predicted values, or the difference between the predicted values and the mean squares, and sum all of them up. And then the third term is called the error sum of the squares, error sum, because there's a regression means there's not a perfect, but it's a best fit. So this means there's an error gonna happen. And what is that? This is yi minus y hat square, and add everything up. The relation between all of them, it's an identity. It's SSE is given by SST minus SSR, which we'll see it down there in a minute. So we want to see what is the coefficient of determination. The coefficient of determination, we use capital R, we use small r square, and it's defined as the proportion of the variation in the observed values of the response variable explained by the regression. So it's defined by the formula SSR over the value of SST, and R square, always the value ranges between 0 and 1, We're going to see what happened as the R value get closer to 0, and what happened as the R square value, not the R, but the R square value gets to 0 or gets closer to 1. So as a quick example here, we can look at, let's say SST is given as 156.0044, and SSR is given as 130.11281. How do you find R square? So R square is given as SSR over SST, and SSR is 130.1281 divided by 156 this is point here, 0044. If you calculate this, that would give us 0.8341. If you get any value below 0 or above 1 or 1, means something wrong. The value has to always be between 0 and 1. So now, how do I find, if we're asked to find the SSE? How do you find the SSE? Well, SSE, as I just gave the formula, SST minus SSR. SST is given 156.0044, SSR 130.1281, and that would give us 25.8763. That's what SSE is. Now, calculation wise, we can look at an example. The book shows here an example of calculation, as you can see. How do we find these values? Okay, so if you remember what was the y hat, we need to find x mean and the y mean, like the mean values. 1 plus 2 plus 3, 6. Divided by 3, that's 2. Y bar is 3 plus 1 plus 5 divided by 3. This is 3. So if the y hat is defined as y minus y bar. So if you do it for the first one, y is 3 minus y bar 3. That's why we get 0. And same thing here. All these numbers came from the previous section. And then all you have to do square y hat minus find y hat minus y bar as well. Square these numbers, and then we find y minus y hat, and then we square them. Why did we do that? Well, because we want to find the first thing is the SST. SST is defined as the y or yi minus y bar square. What is that going to be? What is it? Y minus y bar square. It's this. This is the value. The value of the sum. This is the sum. Is 8. Now, if I want to find SSR, it's good to write down the formula. Y hat minus y bar square. And what is that? It's this, 2. And if I want to find SSE, you can subtract them or find the sum of y minus y hat square, which is this one, 6. From these, I can find r square, SSR divided by SST. What is that going to give us? So r square is 2 over 8. That's 0.25. So the r squared, the 0.25, if you move the decimal point always 2 steps to the right side, that gives you 25, and you can put a percent. So that tells us this means this gives 25% of variation in the observed values, 25% in the observation of the in the variation value in the observed values of the response variable that is explained by the regression. So if, as a note, if so r squared, again, r squared between 0 and 1, as r squared gets closer and closer to 0, then we say the regression equation is not very useful. Is not very useful for making predictions. Not using to make prediction. The same thing, as r squared gets closer and closer to 1, then the regression equation becomes more useful in making predictions. Another way to find the SST, SSR, and SSE is using the following formulas. Some people call it computational formulas. So you can use, this is for SST and this is for SSR. There's a lot of work involved, but it's doable. So we can try to apply this to an example if we want to do so. And I will show you an example on this. So the example, let's say they give me in this table here some x and y values, 8x and 8y values. So what I'm gonna do is try to find the SSR and SST and SSE for these this set of values. The first thing, of course, you want to try to square each y value, which I'm not going to do here, but you square this one, 270 squared, write the number down, 420 squared, write the number down, and then all the way down, and then find the sum. When I did so, I got the sum to be this number. And you can also use an online calculator to find the sum of the squares of a set of values. If you Google it, it will give you a calculator. You just key in the numbers and it'll give you this sum. And I highly recommend you test it out. It helps on the homework. Same thing for the x squares. So if you x squares are easier to do here, like 36, 1, 36, 4, 36, 4, 16, and 25. And if you add them up, you get 158. And also we needed to multiply x by y. So x by y means you multiply 6 times 270 and get a number. 1 times 420, get 420, and all the way down, and then just sum them up, the sum of x, y. If you go through this operation, you get 158. For this, we have 8 values, so the sample size is 8. The sum of all the x values, if you add the first column, you get 32. Add the y column, all the entries in the y column, you get 2,570. The xy that I just spoke about, it gives 9,455. And we are required to find the values of SST, SSR, and SSE. How do you find these values? Well, let's look at the SST first. SST is the sum of the squares of the y values minus the square of the sum of the values divided by n. So we do have the values for this one. We found it earlier, 848,900 minus the sum of the squares, so which is this one here. If you take the 2570 and you square that over n8. So first you do the squaring, divide the result by 8. Then you do this minus this. And we got a value here that is 23,287.50. That's the SST. For SSR, there's more work involved. You need to have a bracket here. Don't forget to square at the end. The product of the XY, which is 9,455, minus the sum of all the x values. We found 32. The same for the y's, divided by 8. And the sum of the squares is 158 minus 158 over 8. And if you calculate all of this, SSR gives 22,687.50. From this, we can find the SSE, which is SST minus the SSR. SST, we found 23,287.50 minus 22,687.50. And this would give us 600, exactly 600. That's what this section is about. It's about finding the square of determination, r square, which again, the main idea is to help us as r gets closer to 0, it will tell us something about the regression equation that we find, if it's really good to use it to make predictions or not. And if it gets closer to 1, yes it is. The closer to 1 the better, the closer to 0 the worse.